afternoon. I am Ken. I am Man Chow, or you can call me Kenneth Chow. This is my quantum gravity series videos, number 16. Today's topic is the creation cycle under the deep Broglie matter waves theory and Chow's Planck Black Hole theory. Firstly, we have talked about the size of the observable universe, as measured by astronomers using the supernovas and this kind of measurement methods, and then they concluded that the radius is 46.5 billion light years, and then the diameter is 93 billion light years. This result is not far. This is from observation by the astronomers. It's not far from the figure computed using Einstein's formula. Einstein once formulated a formula for calculating the radius and the mass of the universe in 1919. I wonder whether he later forgot about it. According to Einstein's formula, there's K log divided by 2 is equal to 1 over R, big R, divided square, and that K is equal to 8 pi G, where G is the Newton gravitational constant, divided by C square, and R is the radius of the universe. And log, what's log? Log is the density of matter in the universe. It's variable from time to time, but is currently estimated to be between 1 to 2 times 10 to the power minus 26, I'm sorry, minus 26 kilogram per cubic meter. And what is the source of this information? Is from the book Selection from the Principle of Relativity by Albert Einstein, and edited with commentary by Stephen Hawking. And this is 2002 edition at page 90 to 91. And also under this formula, there's a mass of the universe is equal to pi square times the square root of 32 divided by k to the power 3 times log, where mass is m is the mass of the universe. And k, as already mentioned, is equal to 8 pi G divided by C square, and log is the currently estimated density of the mass density of the universe. And secondly, after talking about the size of the observable universe, I will talk about the stars and galaxies in the universe, which is, of course, the main constituent of matter in the universe. They are estimated to be not less than, this is estimated not less than quintillions, that is to say 10 to the power 18 of stars forming quadrillions, that's to say 10 to the power 15 of galaxies in the observable universe. What it means by the observable universe is the universe which presently can be observed by astronomers. The farthest limit of this observable universe. Of these 10 to the power 18 of stars, our sun is one of them, and our Milky Way galaxy, and our neighbors, the Large Magellan Cloud, and the Small Magellan Cloud, and the Andromeda. These are the nearest neighbors to Milky Way galaxies. There are several of the galaxies. Next, we have to talk about the radiation from the stars and their development over time. And the first thing is this radiation. The second is we have talked about a topic, a mathematical one, actually a physical one. It's called a virial theorem, and another equation which is called the Oppenheimer-Volkoff Equation of 1939, which was formulated by Oppenheimer jointly with Volkoff in 1939. And these two actually have showed this later on, so they are actually equivalent to each other. And firstly, the radiation of the sun. When we talk about this radiation, we talk about the radiation from one hydrogen atom only. When it reaches the moon, why do I not talk about the Earth, but instead we talk about the moon? It's because the Earth is protected by a magnetic field and also by its atmosphere. The computation, therefore, is complicated. When you reach the moon, has no atmosphere and has no very weak magnetic field, so that is comparatively simple. When it reaches the moon, the radiation from the sun has a mass of 2.35 times 10 to the power minus 54 kilogram, and its temperature is becomes 1.5315 times 10 to the power minus 14 degrees Kelvin. We talk about this is it is the radiation from the sun by one hydrogen atom in the sun. That of course it means the hydrogen atom on the surface of which we call the photosphere of the sun, because the hydrogen atom deep down in the sun, the radiation cannot reach the surface unless after a long period. And when it's the same radiation, when it reaches Pluto is 5.9, more than 5.9 kilometers. The moon is 384,400 kilometers. The average distance is talking about this. When it reaches Pluto, it has a mass from one of the hydrogen atom in the sun of 5.924 times 10 to the power minus 56 kilograms, and its temperature, it becomes 3.8607 times 10 to the power minus 16 degree Kelvin. When it further reaches the Andromeda galaxy, which is 2.5 times 10 to the power 6 light years, that's to say 2.5 million light years. It has the mass provided, of course, over this long journey. It has not been absorbed or been shielded by other astral bodies. Then its mass, it becomes 1.487 times 10 to the power minus 65 kilograms. And its temperature becomes 9.691 times 10 to the power minus 26 kilograms. I mean, not 10 minus 26 degree Kelvin. Well, how do I get this? I got these figures from calculation from my previous video number 8. With that, there I gave a number of equations for calculating this, the mass and the radius, which are called the wavelength, and also the frequency, because it's wave-like. In this equation, then I give E squared is equal to 1.602 times 10 to the power minus 19 coulomb square, all square. And the alpha is 1.1367.036, which is the fine structure constant. And C is the light speed, 3 times 10 to the power 8. 10 to the power 8 meters per second. The H bar is the Planck constant reduced, divided by, that's to say, Planck's constant divided by 2 pi. This will 1.055 times 10 to the power minus 34 joule second. Its unit is joule second. And that the Boltzmann constant is 1.381 times 10 to the power minus 23 joule per degree Kelvin. And the T here represents the degree Kelvin in degree Kelvin temperature. Use this set of equations, then and easily calculate the mass of the radiation and also this wavelength. Please note that I refer to R in the equation as the wavelength. As in the equation, H bar is equal to M times R times C. I refer to R as the wavelength, but usually this is actually it's 2 pi R, which is usually referred to as the wavelength. But because in this set of equations, it's all appearing is the H bar. The H bar is most conveniently used. So just remember that it's usually referred to 2 pi R as the wavelength, and not just the R as the wavelength. But because in this set of equations, it's convenient to use. We all refer to H bar instead of H. Therefore, it's more convenient to use. And apart from convenience, this set of equations gives you it's a commutative actually. That you say if you calculate using the E is equal to mc square by mass times the c square, and then the E will be equal to the H bar 1.0055 times 10 to the power minus 34 joule second times the frequency. It is accurate and must be equal. And this frequency will be equal to R times the wavelength, R times the frequency. It's always accurate. X bar is always equal to the mass times the wavelength, I call it R wavelength, because as I said before, times C times light speed. And E squared is always equal to 10 to the power 7 times the mass times of the radiation times the wavelength of the radiation times alpha, the fine structure constant. So this is a big advantage in using calling the R as the wavelength. Let's look at the figure which I just given before the radiation of the sun when it reaches the moon, the Pluto, and the Andromeda are all calculated out from this set of equations, which I set out in my video 8. Next, I talk about second thing, which is the virial theorem. The virial theorem was already mentioned in my video 3. Why do I still need to mention the Oppenheimer-Volkoff equation? It's mainly because I want to highlight the fact that the same results, which were obtained from two different methods of derivation and by different groups of physicists, they turn out to be the same. The same result were obtained. And this is the benchmark of a correct physical theorem. Firstly, we have the virial theorem, which I introduced in my video 3. And secondly, we have now introduced the Oppenheimer-Volkoff equation. This is the virial theorem, the Oppenheimer-Volkoff equation. When this equation, which are called the equation 17, becomes equal to C squared, and as mentioned in my video 2, equation 17 represents a black hole, and equation 18, the Oppenheimer-Volkoff equation, was derived by Robert Oppenheimer and his assistant Volkoff, using the general theory of relativity. In deriving this equation, Oppenheimer used the general theory of relativity to derive the final outcome of. His purpose was to show what is the final outcome under the general relativity of a gravitational collapse of matter, which is called dust originally we call the collapse of dust, which means very, very minute, extremely infinitesimally minute particles of matter. And then what he's got was the equation 18, this Oppenheimer-Volkoff equation is actually equivalent to this P R equal to one third root C squared multiplied by -1. What is log up here is the pressure, and log here is the density of matter. This equation can further be rewritten as 3 times P divided by log is minus C squared. And so what is the how come the minus sign? The c square represents the kinetic energy, which is negative in sign to the potential energy. And therefore, equation 18, the Oppenheimer-Volkoff equation, also represents the final outcome of a collapsed matter is a black hole. It also represents the fact the virial theorem presents when the final outcome is equal to c square, it is a black hole. The Oppenheimer-Volkoff equation also states that when the final outcome of collapse of minute particles matter, the final outcome is a black hole. As I already shown earlier on, the temperature of the radiation from a star can be cooled to 10 to the power minus 14 to 10 to the power minus 16 degree Kelvin in the interplanetary spaces, which is the space between the planets of the solar system, and in the intergalactic space, that's the space between Milky Way and Andromeda, it can be cooled down to 10 to the power minus 26 degree. You can refer back to my earlier on. Then the conditions for collapse are satisfied. What I mean by conditional collapse is because if it's not cooled sufficiently, the kinetic energy of the matter being collapsed will oppose the pressure and will stay the collapse. The collapse will stop simply. But if it's cool enough, then it will not stop. It will continue to collapse until the final outcome is reached. The state. Which means, under the effect of both the virial theorem and the Oppenheimer-Volkoff equation, the radiation will be, they were and will be collapsed to the Planck Black Hole, and the mechanics of the formation of the Planck Black Hole exhibit the phenomena of the de Broglie waves of matter. Please see in my video 4. Video 4, I introduced the de Broglie matter waves theory. And the formation of the Planck black hole will culminate in the generation of element number 1. That's to say the hydrogen atom. You can refer back to my video 4, the end of video 4 that I gave there a synoptic diagram. At the end of my video 4 for the ultimate final stage of the collapse to a Planck black hole. The final matter I want to talk about is 1. Dark energy, 2. Dark matter, 3. Structure and the mechanics of light. 4. The 4th matter is a photoelectric effect. The 5th matter is the creation cycle. The dark energy is calculated that for each 1 kilogram of hydrogen consumed in the nuclear fusion in the sun, 5.96 times 10 to the power 14 joules of energy is produced and emitted into the interplanetary space. Although it's shown shown above, C1, I've been called C1 above, the mass of the radiation from each hydrogen atom involved in the nuclear fusion becomes increasingly small. As you can see, that my example given is from 10 to the power minus 54 kilogram to 10 to the power minus 56 kilogram, and then down to 10 to the power 65 kilogram, and so on. It's increasingly small. The energy does not vanish, but it's important to note that energy will not vanish, but it will simply spread out in the universe. That is because of the law of conservation of energy. Energy cannot be destroyed, so it simply spread out the energy from the sun. But the sun is only one of the quintillions of stars, 10 to the power 18 numbers of stars in the universe. It was just the energy was spread out of all these quintillions of suns or stars. We only simply spread out and fill the entire universe. Even though the farther is wander from the star itself, the smaller the mass becomes, and the lower the temperature becomes. But it does not vanish; it simply spread out. And then it's also estimated that the total number of hydrogen atoms in the whole universe is at least 10 to the power 80, not 18, remember, 10 to the power 80. And this process of the fusion and emission goes on unceasingly for eons. No one knows how long, actually. I don't know how long. It's certainly more than the 13.8 billion years in the Big Bang theory. It's not that short period of time. It's increasing eons, unceasingly for eons. No one knows how long it has been, the period has been. So the final conclusion is that this must be the origin of dark energy, which amounts to the currently estimated 70% of all the mass in the universe. Next, the dark matter. Dark matter is next important because it comprises 25%, just next to the dark energy. It's also always said that the dark matter are invisible, which cannot be detected except by their gravitational effect, which they exercise on ordinary matter and typically on the visible parts of the peripheral portions of the galaxies. It's also said that ordinary matter trails the dark matter. What in the trails dark matter means the ordinary matter just seem to have been transformed from the dark matter at the same position. That means it trails. What it means by the trails, the ordinary matter trails the dark matter. Then you have dark matter here there, and then the dark matter then transform into the ordinary matters in the same position. That's what it means by trails. You have what you have some authority for this is you have a book called How to Build a Universe by Ben Gilliland of a 2015 edition, and also page 62 of the How Did the First Stars and Galaxies Form by Abraham Lowe. So it is a natural and logical inference that dark matter, which comprises 25% of the total mass of the universe, are pre-matter that is, they will become ordinary matter. One example of this transformation is two ultraviolet photons, each of wavelength 1.975 times 10 to the power minus 7 meter and of mass 1.78 times 10 to the power minus 36 kilogram. That is the energy using E to mc square. Energy 1.6202 times 10 to the power minus 15, 10 to the power minus 19, I'm sorry, joules. What is that? That's 1 electron volt. Then say one ultraviolet photon of the set wavelength and the set mass, the set energy is has 1 electron volt. Two such ultraviolet photons can merge together and becomes what? It becomes a electron neutrino. The electron neutrino is 0.987 times 10 to the power minus 7 meter, and the mass is 3.56 times 10 to the power minus 36 kilogram, and the energy is equal to 3.204 times 10 to the power minus 19 joules. That is 2 electron volts. This process will transform radiation, that is two ultraviolet rays, photons, into a electron neutrino, which is a fermion. Fermion is recognized as a matter, is a form matter. This is how radiation can be transformed into one example. Next, we'll talk about the structure and the mechanics of light. Light is, of course, everyone knows it's electromagnetic waves, and it moves according to the wave equations. Its dynamics instead of the wave equation. It's often said that the light has wave-particle duality, and it's called photon when it is light is a particle. It's often said that the atoms and molecules have the same wave-particle duality. However, according to the experimental results, it's only when the higher the emission frequency, omega, represented by the Greek letter omega, the smaller the wavelength lambda, and the lower the light intensity, that the more pronounced the phenomena in which the electromagnetic waves behaves as a flux of quanta with energy epsilon equal to h bar times omega and momentum equal to p. The momentum is also represented by the letter p. P is equal to h bar times omega divided by c. C is the speed of light, and it's equal to h bar times k, where k is what you call the wave factor, and not as a wave. It's only when the condition when radiation waves behaves as a particle. Is only when it is the frequency, the frequency high enough, and the wavelength small enough, and the light intensity is low enough. The light intensity is concerned with the number of photons. When these conditions are satisfied, it behaves as a particle, but not otherwise. Thus, from the light wave radiation from radio waves, which is of the biggest wavelength, to the microwaves, to the infrared waves, to the visible range array, red, orange, yellow, green, blue, indigo, purple rays, to the ultraviolet rays of long wavelength. Of this range, throughout this range, light remains an electromagnetic radiation, waves, and not particles. How do we know? Because throughout this range, the radiation can be diffused, deflected, reflected. This can only be exhibited by radiation waves. It cannot be exhibited by particles. Particles cannot deflect, cannot reflect, cannot diffuse. It's only from one up to the range of 1 electron volt, as I explained earlier, to 2 electron volts. That is when the radiation waves transform into a fermion. That the radiation begins to exhibit particle behavior. See, now the sixth thing we'll talk about is the photoelectric effect. Now, when the wavelengths of the I still have to see some here. First. The photoelectric effect. When the wavelength of ultraviolet rays diminishes to 1.453 times 10 to the power minus 8 meter, its mass will increase. The wavelength decrease, the mass increase. They are inversely proportional to each other. When the mass increases, the wavelength diminishes. When the wavelength enlarges, the mass diminishes. That's inversely proportional. When the ultraviolet rays wavelength diminishes to 1.453 times 10 to the power minus 6 meter, its mass increases to 2.421 times 10 to the power minus 35 kilogram. That is equal to 2.179 times 10 to the power minus 18 joules. What is that? What is that in electron volts? That is equal to 13.6 electron volts. This amount actually is about 10,000 times smaller than that of the electron. It's equal to 0.0003765 that of an electron. Its mass is about 10,000 times more than the not exactly, but 10,000 times, several thousand times that of the electron. When it becomes that, then the infusion, whenever we infuse such amount of ultraviolet radiation on an atom, on a hydrogen atom, and then you can see the electron from its orbit in the hydrogen atom, and causing a small current to flow. When a large enough number of electrons are freed, then becomes the current. This is the photoelectric effect, or we call it photoionization, and this should be when duality of wave and particle begin. It has both waves and both and particle behavior. At this point. Remember, this is only when it becomes 13.6 electron volts is energy. That the particle wave duality begins, not before. Before it's all still mainly radiation wave. It's only when its mass increases to 13.6 electron volt that's what we call the duality of wave and particle begins. Finally, we come to the creation cycle. That's the main topic of this video, the creation cycle. It's very short. I've only fixed four figures. This is only because the creation cycle is according to my logical and natural inference. It's 100% from the known facts. I draw this creation cycle images, and 0% from anything unknown. Anything not known, I will not add into this figure. So it's so short. We have 100% from known facts. That everything that in this cycle is known from known facts. Firstly, we have the first image. We have the stars emitting the radiation. The stars numbers 10 to the power 18 or more because it's the lower limit of stars. The second image is the radiation, as I say, they cooled down in the intergalactic space. They collapse. The radiation collapse under the virial theorem, which I mentioned, or the Oppenheimer-Volkoff Equation, into Planck black holes. And what are these Planck black holes? Hydrogen atoms. Yeah, I have already explained this in my video 2, video 3, and video 4. And you can refer back to for elaboration. And the third figure is the Planck black holes then form into stars. The Planck black hole, that's to say the hydrogen atoms form into stars. And thereafter, of course, all astronomy books on astronomy mention about this. I talk in details, so I don't need to talk here. They form into stars, and the final figure, the stars emit the radiation. So it's come back to the figure 1. Only 1, 2, 3, 4 figures. Here, figure 1, the stars emit radiation, and figure 2, the radiation, the cool down radiation in the intergalactic space collapse under the virial theorem and the Oppenheimer-Volkoff Equation, which are different. And the first figure, the collapsed radiation forms stars. The first figure. And the fourth figure, the stars emit the radiation. Let's come back to the first figure. Only 4 figures. Very short. This diagram, because I only use known facts and nothing from not known things. Not known. Anything not known, I will add anything. Finally, we have to mention the cosmic microwave background. Actually, in one of my previous video, I think it's video 8. I have already mentioned that what we call this cosmic microwave background, CMB for short, is part of the radiation, which is termed by the astronomers, usually termed the 21 centimeter hydrogen emission radiation, or emission of radiation. And as explained in my video 3, the basic building block of everything in the universe is the Planck Black Hole. Well, you will always have this query: where's the Planck Black Hole? The Planck Black Hole is situated at the center of each and every hydrogen atom. The Planck Black Hole can be detected by its outer shape and structure as the hydrogen atom. The CMB, therefore, the cosmic microwave background, therefore only highlights the fact that the hydrogen atom or the radiation are ubiquitous. The hydrogen atom radiations, the 21 centimeter hydrogen as termed by the astronomer, only the radiation. You will obviously 21 centimeters at big macroscopic object about that size. That's 21 centimeters, and the hydrogen atom is itself is 10 to the power minus 15 meter. It is 1,000th of a 1,000th of a meter. So actually, of course, this is not the 21 centimeter height. Is only the radiation from the hydrogen atom. It's not the hydrogen atom itself. The CMB only highlights the fact that hydrogen atom radiation are ubiquitous in the universe. The universe is therefore constantly changing its overall image, but only bit by bit and slowly. Change in overall image is noticeable only over periods of at least 10 to the power 9, that's billion years. But of course, you will say, what about the supernovas and the nation stars or newborn stars? What about that? Those are they are exceptions. They have rapid changes, which can be noticed within a short time. And this image is consistent with the discovery by the new James Webb Space Telescope, which found that the overall image of the universe, even as far as the edge of the observable range of the universe, is more or less the same as the image nearby to our Milky Way, to our solar system. The last thing, as I mentioned, is the dark energy plus the dark matter is equal to 95% of the total mass of the universe. And both dark energy and dark matter are still in the form of radiation, that is pre-hydrogen atoms. They are pre-hydrogen atoms. Only the remaining 5% are in the form of ordinary matter. That is, the ordinary matter is part of the already completed hydrogen atoms. This includes 4% free hydrogen and helium, 0.5% the stars, all the stars, 0.3% all the neutrinos in the universe, and 0.03% heavy element, so say the asteroid, meteors, etc. These are the whole by today's video. And if you like, subscribe and like.